in the set of all possible instruction sequences which are available in the binary. And therefore, we select only the simplest ones of them because we want to not have the problem that given an instruction provides a useful operation for us, like an addition of 2 registers, we do not want to have this instruction sequence do other calculations or performs memory reads or writes, so that previously executed instruction sequences where operations which we intended to provide the results of those will be overwritten. And another major point of this complete work is we want to be really platform independent. So we're not only aiming at ARM like we discuss in this talk, but we are aiming at all platforms that you can imagine. And therefore, we use the REIL meta language, which is a platform independent meta language that I will discuss with you now in short detail so that you have a basic idea what you can do with it. So what's REIL? With REIL, we have a meta language which we translate all native instructions into. And the REIL meta language is a small RISC instruction set with only 17 instructions, which we're never going to put on any silicon, but we have an interpreter for. And what we do with this is we take an instruction from any native instruction set and substitute it with a graph of REIL instructions. And therefore, we have a platform-independent representation of any instruction that you can find on all of the architectures that you might think of. So basically, we have a whole bunch of arithmetic instructions. We have some bitwise instructions and logical instructions. I think arithmetic and bitwise is kind of like self-explanatory, but the logical instructions you see here is, the first one is byte is 0, so that you can check for whether there is a 0 in one register or not. And the other one is the jump conditional instruction. Then data transfer instructions, so we have a load from memory, store from memory, and a store from register to register. And other instructions like NOP, UNDEF, and unknown. And there's an interesting story about the UNDEF instruction, which actually was not originally intended to be in the REIL instruction set. But due to the fact that some instruction sets like x86 have the behavior that some instructions might undefine flags when run in certain conditions, you need to have this undefined flag to be able to have the same results after interpreting a set of REIL instructions and interpreting the original native code which was translated into the REIL instruction, so that the results of both of the executions are the same for all the native registers on the machine. REIL is completely a register machine and not a stack machine. We kind of like have an unlimited number of temp registers which we need because some of the instructions that we translate, sometimes if you think about count leading zeros or count leading ones and you only want to do it with the small instructions that we have, can end up to be almost as like 60 instructions or something like that for one single native instruction in the original binary code. REIL and its instructions are completely side effect free. That means each instruction only has effects on the registers which are in the definition itself. So there is no flag setting which happens when a REIL instruction is executed. Flags are completely modeled as registers would be also. What does REIL not do? We're currently not handling any exception code. We do not do any floating point. And we currently have no support for 64-bit instructions. We do, though, handle 64-bit memory writes, loads, or arbitrary length of that, but 64-bit instructions are not yet in the REIL translators. So why not? Basically, for a language that is primarily aimed to provide an offensive researcher with the correct tool set to do anything useful, you kind of like have not that much. I currently know of nothing, know of none, floating point instructions which you can effectively use to trigger any kind of bug. Maybe the audience knows more than me, but basically that's it. The no exceptions kind of like comes from that the exception handling in platforms has to be treated architecture independently as well, and we have currently not implemented that yet, so this is one of the further improvements which we can do to the REIL instruction set. So coming back to the original topic of the talk, after introducing you to the REIL instruction set, we're going to now go over the algorithms which are needed to find gadgets in the binaries automatically. We have divided those algorithms in basically 3 stages, so that in stage 1 we collect all the data from the binary which we need for later processing. And in stage 2 we merge this collected data to have it in a state where we can later interpret what actually the contents of the data we have extracted are in a useful manner. And in stage 3 we locate the useful gadgets which we are actually looking for in this merged data. So let's dive right into the algorithms of stage 1. What is the goal of the stage 1 algorithms? First, what we need is, we thought of a way to represent the instructions in a way so that a sequence of instructions can be usefully puzzled together later on. Therefore, we chosen to use binary expression trees, which we extract from the native instructions present in the instruction set of the target architecture. And you can see here on the left what a basic binary expression tree looks like. It's just you have nodes, and they are connected in a binary tree form, and all leaf nodes are operands and all non-leaf nodes are operators. And in this specific case, you add the register R0 to the immediate value of 15. Also, due to the fact that we're not aiming at having single instruction, then return, single instruction, then return-oriented programming, because we think that the overhead of having all those context switches and having like the huge blow-up of stack space that we need for that, we are looking to extract path information from the disassembled binary in a manner so that we can execute instructions sequentially on the path and then use those sequences of instructions to execute the gadgets in our binary. We do this in the following way. For the expression tree extraction, we have a handler for each possible REIL instruction. Most of the handlers are very simple transform, like I showed you already. The addition is just, you can just simply map from the REIL instruction into the expression tree. But for some of the REIL instructions, it is a little special, because for a store in memory, you might have a register or register plus offset to actually address the memory location you have in memory, and you do not want to override this information later on anymore. Therefore, you need a special handler that the uniqueness of this memory store is always kept. We use some kind of SSA to do that. Yeah, and the JCC instruction is the jump conditional instruction, which needs to also be treated specially, because in the case of a jump conditional, we have to treat the condition in the instruction as well. And we deal with this by, we want to always be representing every instruction in a single expression tree. And you can see this expression tree on the bottom of the slide here. And the condition on the left side is the condition for the true branch, kind of, and op is like the operation which will take part. And we use multiplication once on the left side for the true side and on the right side for the false side, so that we invert the condition and later multiply, so only one of the possible outcomes, given the flag is true or false, will be eventually present in the expression tree. We therefore do not have to split the expression trees and all of the other information already collected when we encounter a JCC instruction in the instruction stream. The path extraction is done through a depth-limited search and is done in a reverse control flow order from the bottom of the binary where the free branch instruction is on upwards until we have reached the limit which we have specified in the depth-limited search algorithm. Currently we use values between 15 or 20 instructions depending on the architecture which we are currently targeting and the compiler which is emitting the instruction sequences. So after we have now collected in stage 1 all the data which we need to be able to merge the data, we're going to now merge the data. So the goal of the stage 2 algorithms is basically that we merge the collected data from stage 1, and we do this by combining the expression trees for single native instructions along a path. As I've told you, we have extracted all the possible paths through the instruction stream in the stage 1, and we can now combine them along exactly those paths. Also, due to the fact that our path extraction was from the bottom of the function up to the beginning of the function, we might have taken a path which has gone over a conditional branch, and therefore we need to determine the jump conditions which need to be true when taking this path. And also, due to the way REIL translators work, they have a whole lot of overhead in the translation, and therefore we have introduced some algorithms to simplify the results so that later the matching in the stage 3 gets simpler. How do we do this? To combine expression trees along for single native instructions along a path, you can look at the example that I've just put on the slide. What you can see here is that we have 4 very simple instructions, where the first instruction basically adds R1 and R2 into R0, and then R0 is stored in R4. And what we have here is that given those 2 instructions are encountered after each other, we use the information stored as expression tree for one single register, and as the registers, operands, are always leaf nodes in the trees, we can combine them together because we know that this register has only been influenced by the instructions we just executed. To determine jump conditions on the path, there is the example in the middle of the slide. Given that we encounter an instruction for which the Z flag in this case must be set false, then we generate a condition and put this into the complete expression trees that we have extracted for exactly this path and save it in there as well, so that we can later see that given we want to execute this specific path, this condition must be in exactly this, must be false or must be true. And therefore we can take paths even though that maybe a conditional branch has been introduced while we found the path. Then we need to simplify the results, and as you can see here on the bottom, a REIL translator, this is the original translation of a load from memory where the register was one of the registers in the ARM register set, which was in the end of the register list that the instruction STM has a whole lot of add 4s in there. If you want to match such a tree, it would mean that you would have a whole lot of nodes where all this information is stored in. But we want to have the possibility to use kind of like a fuzzy algorithm to match those. Therefore, we need to simplify the results to have the trees as simple as possible, and therefore we try to use simple algorithms to simplify the result and just like calculate it. Okay. Now that we have merged all the data along the paths, and we have pretty much for every path that we can execute all the information, how registers, memory locations, and jump conditions are influenced, we can now start searching for the specific gadgets that we are actually aiming to find in the binary. And one of the parts is that we use a tree match handler for each of those operations. So what we basically do is take a tree and try to compare it to some tree that we have earlier defined to see if it matches. I'm going to show a result later on. And then, due to the sheer number of gadgets that, like in a normal library, if you would take libsystem from the iPhone, for example, I think it's like 240,000 gadgets that you can find in there with those algorithms. We only want to select really the simplest possible gadgets that are available to us, so that we don't have to later on in the compiler stage work with so many side effects that on one hand the compilation time would take forever, and on the